All right, welcome to the first video in Chem 241, Intro to Analytical Chemistry. So the point of this video is really just to give you a quick view from 10,000 feet. What does this subdiscipline analytical chemistry constitute? How does it fit into the other subdisciplines that you might have been familiar with up to this point, like organic chemistry, maybe inorganic, etc.? What are the big questions in the field right now if you're conducting research in the field of analytical chemistry? And then what are the goals of this course? Why is it an introduction to? So what are the general takeaways that you can expect to see in the course? So analytical chemistry is this massive subdiscipline. It may not feel that way to you, but it's probably the largest subdiscipline in chemistry. It's also the most employable. It's where most of the jobs exist, because you think about it, analytical chemistry, really, its central premise is the measurement of chemical or biochemical species. And that can be in any medium. That can be in the human body. That can be in the environment. It can be in a chemical research lab, whether you're doing synthesis or anything. You have to have tools and you have to have techniques to know, well, how much of that stuff do I have? You also have to have techniques that allow you to identify if there's even something there to begin with. So how do we even invent and begin to design these tools that allow us to study whether or not a compound even exists on this planet or in the universe, etc. So analytical chemistry is this massive field with a huge charge, multiple facets in terms of the questions that are central to its theme. And so I'll just walk you through a few. So a lot of modern measurements are going to be done through wearable devices. And so I just grabbed this image from the internet, but it sort of summarizes all of the possible either implantable or wearable devices that are currently being developed for monitoring certain aspects of our own health or biometrics. Every single one of those devices is centered on analytical chemical measurements, and we're part of an analytical chemistry research group. That may also include biomedical research engineers and biochemists, etc., but all of the central measurements are conducted under the realm of analytical chemistry. Another example I have here, which actually comes out of your textbook, but I think is just a neat example of some of the more exotic examples of analytical chemistry in modern days. And actually, this isn't really modern. This is probably 10 or 15 years old now, but this is a really tiny device. It's a cantilever made of silicon, and you can see that the scale bar here is 2 microns. So the width of this thing is less than a micron. So we're talking hundreds of nanometers. So we're talking 100 times thinner than, say, your hair. And this thing is free floating in space, and there's a tiny little gold dot right there, and on that gold dot the researchers did some interesting chemistry with these cysteine residues, or these thiol residues, and by adding those onto the surface, they can look at binding of particular species with that sulfur residue, because sulfur binds nice and tight with gold. What they can do is they can actually monitor the oscillation frequency of this tiny little resonator in space, and they can measure down to single molecules. So this is like an analytical balance that you've used in probably many of your chem courses, except it's done on the nanoscale and allows us to measure things in the attogram scale. Tiny things. But this is an example of taking analytical chemistry concepts and sort of taking it to the extreme. These like almost single molecule measurements. Other sorts of biological applications, one of the huge areas of analytical, at least traditionally, it's still big but less now, but a huge commercial area has been glucose monitoring because of the large population of type 2 diabetics in this country and globally. Glucose may seem easy to measure, but it's actually pretty challenging if you think about the construct of the molecule and then the complication of the fact that it's usually residing in this mixture of biomolecules of proteins and cells and things like that. So how do you actually measure that? So most of the commercial measurements now use these little strips that are based on an electrochemical or electroanalytical measurement. That's when you prick your blood and you put a drop right here. This is some classic what we call amperometry, which we'll talk about later in the class. But there's also a variety of other methodologies that people are utilizing these days, implementing electrodes directly onto a contact lens and doing electrochemistry on glucose that's in your tears. That's a really non-invasive way. A mouth guard, looking at saliva, a sticky patch that can use sweat to analyze, or these sort of needle-type glucose sensors. There are these microneedles that sample just the epidermal layer of your skin, which is still considered a non-invasive method. All of these are rooted in analytical chemistry. They all require us to think about how to measure an analyte, the thing of interest, in this case glucose, in a variety of complex mixtures. That may involve separations, that may involve spectroscopy, that may involve electrochemistry. All of those fit within the wheelhouse of analytical chemistry. The last thing I'll mention is just environmental applications, because this is almost its own field. It's so massive. And we'll talk about several examples in this class. One that I like to teach with in Chem 241 is the Flint, Michigan water crisis. And thinking about, well, you've got this stuff, lead, in water, but it turns out lead can take on a variety of different chemical species. It can complex and bind to so many different things. So how do you know what you're measuring, and how do you do it safely and efficiently? And how, if you wanted to, how could you let people in the communities themselves measure lead rather than requiring them to pay to send it off to a facility? And so environmental analysis, monitoring chemicals in the environment, is a huge field. Right? Climate change, measuring gaseous or aerosol species in the atmosphere, all analytical chemistry. And so that's going to be sort of the view from way up high in this class, is really thinking about the broad sets of applications that pertain to the subdiscipline. So the specific goal of this course, because as you can imagine, it can take more than a lifetime to actually learn all that analytical chemistry has to offer. It's a huge field, bigger than any other subdiscipline. But what you're trying to do in this course is to develop an intuition about chemical measurements specifically. So when you think about, what is an analyte? And what about the analyte lends itself to different methods of measurement? Can we measure that thing with electrochemistry? Can we measure it spectroscopically, meaning does it have color? Does it absorb light? How do we separate that thing, that analyte, from a mixture of other stuff? So that's where we're starting to develop an intuition. When you hear about a chemical or you see a structure of a compound, how do you start to think about, well, what might I leverage? What functional group might I leverage to pull it away from other dissimilar compounds? Or what functionality or moiety, maybe a conjugated system, allows us to shine light on it and get it to absorb light? Or maybe it's easy to pull an electron off of it and utilize redox for the measurement of this thing. And then goes along with that, or what are the sort of figures of merit that tell us whether or not a measurement is good? Things like accuracy, precision, and some basic comparative and descriptive statistics. So you've all seen statistics, and this is not a statistics course, but I'll introduce a little bit, and how we use statistics to evaluate whether or not we should use spectroscopy versus electrochemistry for the measurement of a particular analyte. How many times should we measure it to feel confident? What is confidence? If we're trying to report back to a community in Flint, how confident should we be? How confident can we be when the impacts are central to the human health of actual people? Those are the types of things that we want to think about in this course. So traditionally, the field of analytical chemistry, I mean, it can be subdivided in a variety of different ways from different perspectives, but the way it's often taught and thought of is sort of these two larger subcategories, which constitutes wet chemistry or wet chemical methods of analysis versus instrumental methods of analysis. These are sort of the big areas, and we're going to talk about both, but we're going to focus about the first 2/3 of the course on wet chemical methods, and the last 1/3 of the course on instrumental. And then if you're interested, I highly recommend going on to take Chem 342, which is Introduction to Instrumental Methods. So this class will serve sort of as a springboard to instrumental, Chem 342, but there's an entire course, and honestly should be multiple courses to get you more versed in instrumental techniques. So what do I mean in terms of the difference in these two subcategories? So with wet chemistry, we're talking about things like titrations. Those can be acid-base titrations, which is primarily what you may have had experience with in a previous course. There's also precipitation reaction or titrations. There's redox titrations. There's a version of a titration for virtually any type of reaction, but when we affix it to a titration as a method, then we're using precise and accurate volumetric analysis to determine something about that particular chemistry, often the concentration of a species. So titration / volumetric analyses, those are a huge part of wet chemistry. We can have gravimetric analyses, which is by mass. So that's reacting things and then measuring them very accurately, filtering them out, and then weighing them on an analytical balance. And then we can have some electrochemistry. Electrochemistry is sort of a in-between area where it's almost instrumental, and sometimes it can be, but it's in its basic form. We can have things like potentiometry, where we're measuring the voltage of a solution, and that tells us something about the concentration often. So these are sort of the big areas of wet chemistry. So you're using glassware, you're using liquid, solid reagents, you're doing reactions, and then you're often using mass or volume and sometimes voltage to evaluate something specific about your chemical system. Instrumental analysis is a little bit different because it moves towards fully automated, often electronic-based instruments that may use some principles from wet chemistry, but they're typically more advanced in their analysis capacities. So we're talking about things like spectroscopy. Spectroscopy is the interaction of light and matter. So this is an IR spectrometer. If you've taken organic chemistry, you've used one of these. This is infrared absorption spectroscopy. This is an NMR, nuclear magnetic resonance spectrometer. This is a specific type of radio frequency spectroscopy. This object here is what we call an ICP-AES, which stands for inductively coupled plasma atomic emission spectrometer. So this is atomic spectroscopy. This is how we measure things like lead and drinking water. So instrumental analysis are all the big fancy tools, things like GCMS and HPLC and lots of different hyphenated acronyms that we'll talk about or introduce you to a little bit later in the class. You may have had exposure to some of these, but this class will introduce you to how they work and why you choose one versus the other. So this is the big breakdown of the subdiscipline.